Hello, everyone, and welcome. So today, we're going to start a very important topic from Unit 14, Semiconductor Electronics. The topic is the semiconductor diode. Now, I know it can seem a little bit tricky, but don't worry. I will make it so simple and so clear that you'll be fully prepared for your exams. Cello, let's begin. First, a simple question. You plug your phone charger into the wall every day, right? But have you ever stopped to think about what's actually happening inside that little box? The current from the socket is AC, but your phone battery needs DC. So how does your charger do that conversion? Well, the secret, the magic, you could say, is all thanks to a tiny but very, very powerful component. It's like an electronic gatekeeper, and its name is the diode. This is the real hero inside your charger, and actually inside almost every electronic device you own. So what is this diode, fundamentally? The simplest way to understand it is to think of it like a one-way valve for electric current. You know, like a valve in a water pipe that only lets water flow in one direction and not the other. A diode does exactly that, but for electricity. It's a very simple but very powerful idea. Let's break it down. When the current is flowing in the, let's say, correct direction or the forward direction, the valve just opens up and lets it pass through, no problem. But the moment the current tries to flow backward in the wrong direction, that valve slams shut. It's blocked completely. It's basically a one-way street for current. Okay, so here's the formal bookish definition you need for your exams. A semiconductor diode is a p-n junction device that conducts current in one direction, which we call forward, and blocks it in the opposite direction, which we call reverse. The most important part to remember here is this one-way behavior, and it all comes from something called the p-n junction. But how does it actually do this? I mean, how does the diode know which way the current is flowing? The whole secret is inside it. It's all about an internal barrier that gets created right where the p-type and the n-type semiconductor materials meet, at the p-n junction. And the best part is, we can actually control this internal barrier. How? By applying an external voltage from a battery. This process is called biasing. So we can either forward bias the diode to let the current flow, or we can reverse bias it to block the current. So let's look at this comparison. It makes it very clear. In forward bias, we connect the positive terminal of the battery to the P side of the diode. This external voltage pushes against the internal barrier, making it smaller. And what's the result? Current flows easily. The valve is open. Now in reverse bias, we do the opposite. We connect the negative terminal to the P side. This actually helps the barrier, making it even bigger and stronger. So the current is blocked. The valve is shut. Simple, isn't it? You know, every electronic component has its own report card that tells us exactly how it behaves. For a diode, this report card is called the IV characteristic curve. It's just a graph that shows us the relationship between the current, I, and the voltage, V. So let's have a look at our diode's report card. Let's start on the left side of the graph. This is for reverse bias, when we apply a negative voltage. Now look closely at that line. It's almost perfectly flat, right at zero. What does that tell us? It means practically no current is flowing. The valve is shut tight. Okay, now let's look at the right side of the graph, for forward bias. When we apply a small positive voltage, you can see that nothing much happens at first. The diode is, well, it's waiting. It's waiting for a special turn-on voltage. For the most common type of diode, made of silicon, this magic number is about 0.7 volts. But the moment we cross that 0.7 volt threshold, everything changes. Look at the graph. The current suddenly skyrockets. It shoots up almost vertically. This exponential jump tells us that the barrier has been completely defeated. The one-way valve is now wide open, and a huge amount of current can flow through. And this really shows you how powerful the diode is. Think about it. With a tiny forward bias of just 0.7 volts, a typical silicon diode can easily allow a current of 0.4 amps to flow. That's a massive amount of current being controlled by such a small voltage. Okay, now for a very important section. Let's talk about some common mistakes, some traps that can make you lose marks in your exams. I call them silent killers because they seem simple, but they can be tricky. But don't worry, once you know them, you can easily avoid them. So what we're going to do is we're going to bust two very common myths about diodes. We'll compare the myth with the reality. Getting this right is absolutely crucial for scoring full marks on any question about diodes. Okay, myth number one. A forward bias diode is a perfect wire with zero resistance. This is wrong. In reality, it is not a perfect wire. There's always that voltage drop of about 0.7 volts across it, and it has a small internal resistance. Now for myth number 2. A reverse bias diode has infinite resistance and absolutely zero current. Again, not quite true. In reality, it has very, very high resistance, yes, but a tiny, tiny leakage current still manages to flow. It's almost zero, but it's not exactly zero. Remember these small details. They show the examiner you really understand the topic.
So, we've understood how a diode works, we know about biasing, we've seen its IV curve, but what's the big picture? Why is this simple one-way valve so important? For that, let's go all the way back to our first example, the phone charger.
Here's the most important application. This unique one-way property of the diode makes it the perfect tool for a process called rectification. And rectification is just a fancy word for converting AC to DC. Every single one of your electronic gadgets, from your phone to your laptop, needs DC power to work. And it's the humble diode that makes this conversion possible. All right, let's quickly summarize the key points you must remember for your exam. 1. A diode is a PN junction that's like a one-way valve. 2. Forward bias opens this valve. 3. Reverse bias closes it. 4. A silicon diode needs about 0.7 volts to turn on. And 5. Its main number 1 job is rectification, converting AC to DC. If you remember these 5 points, you are all set. So, we've seen how just one PN junction can create a device as powerful and as essential as the diode, a device that literally enables all of modern electronics. This leaves us with a very interesting question to think about. If one PN junction can do all this, what incredible new things could we do if we combined 2 of them together? We'll explore that in our next session.